Hello students, welcome to the channel. In this basics explained video, we look at exponential function. We try and understand what this function means, the formulas that we use for this function, and how do you interpret the various variables that make this function. So the exponential function is a function of the form fx is equal to a times b to the power x, where a and b are constants. A should be non-zero, b should be positive, and b should not be 1. Now, there are two kinds of exponential functions. One represents exponential growth when the base of the exponent b is greater than 1, and the other is exponential decay when the base b is between 0 and 1, right? So for example, here you have the graph of y is equal to 2 to the power x. So you can see that at x equal to 0, y would be 1. So the y-intercept is 1. At x equal to 1, y would be 2. At x equal to 2, y would be 4, and so on. So as x increases, y increases quite rapidly, and so the graph increases rapidly, right? If, on the other hand, you have b between 0 and 1, then you notice that at x equal to 1, y would be 1 by 2. At x equal to 2, it would be 1 by 4. And so the decline is also precipitous, right? So one interesting thing is that the y-intercept for an exponential function is the value a, because when x is 0, b to the power 0 becomes 1, and the y-intercept becomes a. Okay, we have also plotted 3 into 2 to the power x, which means that the y-intercept here would be 3. And here we have plotted 3 into 1 by 2 to the power x. Again, the y-intercept is 3, but this is a falling graph. Now, a lot of times you would be expected to understand the difference between linear growth and exponential growth. And there would be questions that expect you to identify this difference. So linear growth is growth where the y value increases by the same amount. And exponential growth is the one where the y value increases by a constant ratio. So we know that the linear equation is y equal to mx plus c. So if I plot x and y, at x equal to 0, y is c, the y-intercept. At x equal to 1, y is m plus c. At x equal to 2, y is 2m plus c, and so on. So as I increase x, I notice that y increases by a constant m every time, right? So it gets added, m gets added every time, and this m is known as the slope of the linear equation. Now consider the exponential function y equal to a times b to the power x. At x equal to 0, the function is a, which is the y-intercept. At x equal to 1, the function is ab. At x equal to 2, it is ab squared. At x equal to 3, it is ab cubed, and so on. So here, as I increase x from 0 to 1 to 2, I notice that the value of the y function gets multiplied by a constant b, right? So here we notice that the ratio of the corresponding y values is constant, unlike in the linear curve where I was adding a constant value, right? So this is the primary difference between exponential function and linear function, and we will look at some questions where this difference is explored. Okay, let us also look at the exponential growth formula. This is also known as the compound interest formula. If I have an initial value p that grows at a rate of r% per year, then the final value a after t years is given by p times 1 plus r by 100 whole to the power t. So for example, let's say I invest an initial amount of 1,000 at 5% rate of return for 10 years, then this would grow to 1,000 into 1 plus 5 by 100, which is 1.05 to the power 10, which comes to 1629. This part, the base is often known as the growth factor. So a normal representation for this formula is A is P times the growth factor to the power T. Now, what happens when the growth is not annual but occurs every k years? In that case, k becomes the denominator of the exponent. So here the formula would be p times 1 plus r over 100 to the power t by k. So for example, if the 5% rate of return was not annual but was applicable every 2 years, then my answer would be 1000 into 1.05 to the power 5, because I would say 10 divided by 2, because it's applicable every 2 years. Okay, what about exponential decay? When we speak of exponential decay, instead of the plus sign within the bracket, we take the negative sign. So the formula becomes A is P times 1 minus R by 100 whole to the power T. Right, so how do questions on the SAT look? So for example, the first question, after a new car is purchased, the value of the car is modeled by a function that decreases exponentially over time. Which of the following could describe how the value of the car changes each year? So let's work with the options. If the value of the car is 800 more than the previous year, then this indicates a linear growth. So it can't be A. If the value of the car is 800 less than the previous year, this is a linear decline. So again, it's not B. If the value of the car is 8% more than the previous year, then this is exponential growth, right? So again, it's not C. But if the value of the car is 8% less than the previous year, then it is exponential decay. So here the answer would be option D. So in such questions, you have to see whether the growth is happening by a constant amount or a constant ratio. If it's a constant amount, it's a linear growth. If it's a constant ratio, it's an exponential growth. And then you also have to check whether it's increasing or decreasing, and that will give you the result in terms of whether it's growth or decay. Question 2, a group of students participated in a study. It was determined that for each hour of experience performing a certain task, the time necessary for each student to complete the task decreased by 5%. Wendy took 30 minutes to complete the task with no experience. Which function models the amount of time in minutes it will take Wendy to complete the task after X hours of experience? So we work with A is equal to P times growth factor to the power T. So here the initial value is 30 minutes because when there was no experience, Wendy took 30 minutes. And the growth factor would be 1 minus 5 by 100. Because with every hour, the time necessary to complete the task decreases by 5%. So it's 1 minus 5%, which is 1 minus 0.05, which is 0.95. So my growth factor is 0.95. So the final amount of time it would take would be 30 times 0.95 to the power X, where X is the hours of experience. So that's 30 times 0.95 to the power X, option C. Okay, the given function models the number of flower beetles in a certain area where T represents the number of days after June. Which of the following is the best interpretation of the number 1.11 in this context? So this is the growth factor, right? Which means that the beetles increase by a factor of 1.11 with every day in June, right? So option A, the model predicts that there were approximately 1.11 flower beetles in this area on June 1. No, that's the initial value, that is 100, not 1.11, so that's not correct. The model predicts that the number of flower beetles in this area increases by approximately 1.11. No, this would indicate a linear function, so it's not B. The model predicts that it will take approximately 1.11 days for the number of flower beetles to double. No, that's not correct. 1.11 is not time, it's the growth factor. The model predicts that the number of flower beetles grows by a factor of 1.11 each day. So that's exactly what we want. So it's D. What is an equation of the graph shown? Okay, so we'll first figure out the y-intercept because the equation is in the form a times b to the power x, and a is the y-intercept. So this is 0 to 10. So this would be 2, 4, 6, and 8. So the y-intercept is 2, right? So if the y-intercept is 2, then I can say that it should be 2 times b to the power x, right? And the only option which is in the form of 2 times b to the power x is option B. So let's verify. If I say 2 times 3 to the power x, when x is 1, y would be 6. And indeed, that is correct. And when x is 2, y would be 18. And yes, that is also correct. So the right answer is 2 times 3 to the power x. A sample of strontium-90 will radioactively decay to half the original quantity in approximately 29 years. The function S above models the amount of strontium-90 in grams that remains T years after a 10-gram sample starts to decay. Which of the following is the best interpretation of the number 0.5? So here we are seeing that it decays to half the original quantity in 29 years, which is why 29 is the denominator of the exponent. And 0.5 here is the growth factor. So because we know that it decays to half, right? Which is why 0.5 is the growth factor. So the approximate number of years it would take for 5 grams of strontium-90 to remain in the sample. No, this is not years, it's the growth factor, so it's not A. The proportion of strontium-90 that remains after 29 years. That is correct because after 29 years, 1/2 of the strontium would remain. So that would be 0.5. So this is my answer. The number of grams of strontium-90 in the sample that will decay approximately every 29 years. No, the number of grams is not fixed. It will depend on the starting value. So it's not C. The number of grams of strontium-90 by which the sample will be reduced each year over approximately 29 years. So this again is not correct because it's not the number of grams as we discussed, it's the factor by which strontium-90 would decay. So it's B. Right, so that was a quick explainer on exponential function. Hope this exercise helped. If it did, hit like and subscribe to the channel. I'll see you guys in a new video soon. Take care. Bye-bye.